presentation about the method in extreme climate analysis and also the applying climate information for decision support services. So in the first part, we're going to have a lecture from Dick Arndt. So he is the chief scientist of NOAA's climate monitoring scientist. And after that, we're going to hear from Marina about the applying climate information for decision support services. And she is the climate services program lead, National Weather Services. So for each presentation will be delivered 20 minutes each. So now is already 21st past 8, so it's already time. So for the first lecture will be delivered by Dick Arndt. Time is yours, Dick.
Hello, thank you, and thank you for having me tonight. I appreciate the opportunity to join, and I am really excited to see my colleagues Marina and Kathy present as well. So we all work in different parts of NOAA, different offices within NOAA. We don't get to work directly with each other quite a bit, but we deal a lot with each other in climate services and climate data. So I'm really excited to hear them. I'm going to share my screen shortly, but I wanted to say this is largely from a climate services perspective. What I was asked to share is how we work with extreme events in NOAA, and how we try to help define them for interpretation or understanding for our customers, for our citizens, and methods that we use in a services way that may look familiar, especially if you've worked with some WMO techniques before, that can kind of share and provide some context for your customers, for your citizens. So I'm going to try to share my screen here. And I think I have it. Okay. Did that work?
Yes.
Okay, great. All right. So I'm Dick Arndt. I am the chief of our Climate Science and Services Division. I've been on the job for about 15 days, so I'm brand new. Before that, I spent 11 years as the chief of our climate monitoring group. And much of what we'll talk about today comes from the climate monitoring experience that we have. I'm happy to be here. I'm from one of the data centers within NOAA. So I think, yeah, there we go. So I'm with the National Centers for Environmental Information, and NOAA is kind of strange in that our climate services are spread across our agency, and we don't really have a central place to provide centralized climate services. So several offices around the country in different parts of NOAA handle different pieces of our climate services work. We are the agency within, or the office within NOAA that handles much of NOAA's data. So a lot of the data from our weather service, from our ocean service, and from our fisheries service will wind up at one of the 4 centers that you see here. My center is here on the right in eastern US, Asheville, North Carolina, and that's where the weather data goes. So we handle a lot of the National Weather Service's data. And we work with the Weather Service and our other partners with NOAA to turn that back around and provide context for today's events on what's going on. And so we have, and I don't know how to undo my pencil here. There we go. So just some, I don't know what I'm doing here. Okay, so just 3 examples from our climate services activities that we do, and then I will probably not take up the whole time, And if we want to talk and share, I'm happy to do that. So, so the three examples, as one is we'll talk about how we try to characterize or display our extreme events for better understanding by our elected officials and by our citizens, and what we do to try to transform the data to make it easier to interpret for very busy officials. Then we'll talk about our National Climate Extremes Committee and how we adjudicate or determine record values for our country. And then the same function in the State Climate Extremes Committee, which is actually a lot more active, and it helps determine what are the extreme events that occur for each of the states that make up the United States. And that's where we'll go. Okay, so an example of a very extreme August that we just had temperature-wise. So we're going to look at 3 maps, and they're all the same data, but we just represent it in different ways to help different pieces of our public get what they need out of it. So this is a map of just simply the average temperature for the month of August 2020, last month, on a grid across the United States. It is it is in degrees Fahrenheit. I apologize for that, but these were the average temperatures for the U.S. So up there in quite warm. So this is one way of displaying our data, but that doesn't really say how extreme this was. So we take different measures with the data, as I'm sure you do too, to try to help people understand whether this was unusual or extreme. So the next method that we do is just compare that that observed value to a historical baseline. So this happens to be August 2020 compared to all of the August months of the 20th century, so 1901 through 2000. And we use this legend on the bottom that shares how many degrees Fahrenheit warmer or cooler than normal that was. And that helps put some context for our people who have a climate background that they can use. So we can see that the month of August was 6 to 9 degrees Fahrenheit, which is what 4 to 6 degrees Celsius warmer than the average for August, which is quite warm in an already warm part of the country. And that helps at a glance convey how much different this August was versus historical patterns. Finally, the last thing one of the last things that we do is we try to provide an estimate of how unusual that is. So we start with the observations, the actual temperature, then we describe how much warmer or cooler this is than a baseline or an average August. And then what this map is showing is how unusual that is, where that stands in its historical record. So the places with this darkest red, record warmest, had the warmest August of their record. And for the continental US, the 48 states see here, our record goes back to 1895. So it's about 126 years of data. Where you see red in the southwestern United States, we did have the warmest August on record. It was also quite dry. We would do the exact same things, or we do the exact same things with our precipitation maps. And so a very warm and very dry August out west led to some rapid drought intensification and has fed into much of the fire issues that we've seen, especially in the central and southern Rocky Mountains in the southwest US. So what these categories describe, it's much like if you've worked with the WMO's ClimDex methods. Record warmest means that it's, of course, the warmest on record. Much above average corresponds to the WMO's top 10%, 90th percentile. So warmer than 90% of Augusts in history. The third shade from the right is a light orange, and that's above average. And that would be the top tercile, the top 1/3 of Augusts of history. The middle is the middle third, so the middle third of history. And then likewise, as you go into the cooler shades, the cooler third of history, 1/3 of history, 33% of history. The second to last is the coolest 10% of August on record. And then the last color, the darkest color, which we didn't use in this August map, is anywhere that would have had a record coldest. This is a very obviously simple to understand method. It's very useful for our customers, our politicians, our managers, people who are working on kind of more complex issues and don't have the time to plug in just how extreme this was. We like to express it or communicate in this way to help make it simple for them to incorporate. So that's a philosophy we use all across our climate monitoring suite. Is we first share the observations. Second, we compare that to a baseline. Is it above or below or drier or wetter than normal? Third, we try to find a way to describe how unusual that is. As scientists, we would all use standard deviation, +1 or 2 standard deviations. But with the public, that's just too challenging. So what we try to do is use ranks like these to describe where they fell into history. Two other things that we do: we have a national climate extremes committee that we adjudicate or determine our national climate records. And this is a partnership between my office, my old office, the National Weather Service, and the American Association of State Climatologists, which are kind of the lead climatologists for each of the states that in our country. And we work together to help determine what these values on the right. And this table, if you go to the link, is about, there are about 30 or 35 records, national records. And we work as a jury of 3 people, but also informed by many experts from the outside to determine whether an observation has broken or established a new record in the United States. And we look at things, so here are some of our national records. Our most recent one is 24-hour rainfall. We had about 1,200 millimeters in Hawaii, April of 2018, which is quite a bit for the US. That may not impress Indonesians, but it was a lot for us. That was our newest national record. What we do is each case is different, but we essentially ask these questions to determine whether they're valid. Was the measurement meteorologically plausible? Meaning, did the meteorology of the day, could it have produced a big event like this? So one of the things we look at are all of the weather maps for the event that we're looking at, and ask the question: could this have produced an extremely wet day? Could this have produced an extremely hot day? And this helps us kind of screen or filter our cases to make sure that they weren't just bad observations, that it actually could have been supported by the weather. The next set of questions we ask are just a comparison. Have we looked through our entire record again and determined that this new observation does indeed exceed all of those? That seems like it actually is a very straightforward thing to do, but there is a lot of data and a lot of records, and all of us around the world increasingly are digitizing more and more of our paper records. And so it's a good time to go back and see if our new digital data have any records that would exceed this. And then the last thing we ask is will this value be archived properly for examination later? And that means, did it come from a purpose-built station? Was it measured by a legitimate observing platform, or did the observation come from something where we can't really capture that data and it was just reported by someone? And so we really try to investigate the equipment used and who handled that data along the way. On the right here are some examples of some recent reports that go along with any of these determinations, whether they were approved or whether they were declined. We write up the report, and this is why we made the decision. And that way someone can come back years later, if they question one of our determinations and reopen the case. And we actually, our warmest temperature in the US, which is also the warmest temperature historically for the globe, is a very controversial temperature. And so I would very much expect that that will get looked at again. So we try to provide all of our decision-making material for future investigators. Probably the most useful, practical records examination that we do is for the states. And so for the states, we look at 5 or more categories of meteorological data to establish a state record. These juries, these committees are made up of someone from the climate monitoring shop, my old office, the local forecast office from the Weather Service, the regional office, that state's state climatologist, and our regional climate center that serves that part of the country. And we do a very similar process, but we record many records for our different states. And you can see in alphabetical order, some records that we have for Alabama, then Alaska, then Arizona, and so on. And the list is very long for 50 states. But each of these has an investigation behind it, has some documentation behind it. And the reason we do these are because they help the states understand how extreme their climate can be. So for engineering standards, or for curiosity, for particularly for infrastructure engineering, it's important to know just how hot it can get or how cold it can get in the state. And these records help define that with authoritative records. They also help the science because we examine very, very extreme values and we make sure that they're legitimate or at least plausible. And that helps us in our climate studies with cleaner data in the extremes, because that's where one bad data point can really mess up an exacting analysis. So that's one of the values. That's why, part of why we do this. And then finally, they help us identify problems with observing practices. So many of the records are simply due to maybe an observing station that was managed improperly, or an instrument that malfunctioned, or some other event to the station. And we can often work with each other to identify things that may be happening at some of our stations and help come up with policies or recommendations to help keep the standards of the observing practices very high. And that is also very important for climate analysis, is to make sure that we continue to have a rich tradition of good observations. So this is a hail record from Alabama. And so this is one of the things that we don't want people to do, is don't grab it and hold it and take a picture with it. You know, put it in a bag and put it in a freezer, and don't let it melt or sublimate, so it shrinks, so we can really get a good understanding. So one of our investigations actually led to a National Weather Service document on how to handle really big hail. And it's actually a really good document. We do post all of these investigations on the web for our customers, again, so that they can examine what we did. And each one of those links would have a report. So about a 15 to 20 page report that says, here's what we looked at, here's what we decided, and so on. And here's who participated. So why do we do all that? Those seem very straightforward. They're quite simple compared to the climate science that you already do. But the reason we do these is we want to increase the confidence in our understanding of extreme observations. We want to make sure that the really big extreme observations are good observations, and we can tune our understanding of the extreme weather climate using that good data. It really helps us build partnerships among our partners. So the different agencies or offices within NOAA that work together, we often build a lasting relationship and a more comfortable relationship to work alongside each other. And then finally, we identify improvements for our observing systems. And that's why we do that. It seems fairly straightforward. It is very straightforward. There's nothing really tricky about it. It's just good work that helps make our data better, and it helps improve the services that all of our NOAA agencies can do. And I think that's all of my time. Oh. And I very much appreciate it.
Yeah, Very nice talk, and thank you because you are really in the proper time. It's
Yes.
a 20-minute presentation. So at least we already hear everything from Dave. That's very inciting about the importance of the extreme documentations, extreme event documentation. So we got from him that observation data is very important, and then statistical methods, it's also very important, and then documentation and the archiving is also very important also in the climate extreme analysis in the end. But I know that all people already have many questions, so please type in the chat room. Actually, you can also raise up your hand, and then you can have chance after Marina presents her presentation. So we continue with the second speakers in this session. We have Marina Timofeyeva. So she is Climate Services Program Lead National Weather Services. So basically she manage NWS strategic and operational planning process in climate services. So she will talk about applying climate information for decision support system. It's also very important for us in the climate services in BMKG, because right now, maybe for your information, Marina, that we already run our climate early warning system here in BMKG. So maybe if you have chance to visit us here, so we're going to show you our early warning system regard climate extreme. So Marina, time is yours. Please use your time.
Thank you so very much for the introduction, and I'm thrilled to be here, and I'm very grateful that Dick and Kathy, that who will follow me, my colleagues from NOAA, were able to join us. Seems like, you know, we're going to have a nice, good session. I'm going to make a link now, probably between what Dick was introducing to you and what Cassie will be talking about. Why do we do climate services? So can we go to the second slide, please? Can you advise my slides? Thank you. Thank you so much. We're talking about impact-based decision support services, because whatever we are developing with our climate information, whether it is data or analysis results or outlooks, this is all our tools for provision impact-based decision support services, which includes provision of observation and forecast information, preparedness education, interactive interpretive state services for core partners, whether it is National Weather Service in the United States or any kind of national meteorological and hydrological institutions in any country. In IDSS might be impact-based decision support services can be characterized as episodic, which we do when there is a big climate events. For instance, in the United States, a big impact is ENSO, El Niño Southern Oscillation, or when it is recurring, like any kind of heat waves that is coming very often. We are working, they can be recurring events. Can we go to the next slide, please? When we talk about climate specifically DSS, which includes engagement, collaboration, and provision of interpretive service of subseasonal to seasonal information to federal, state, local, tribal, territorial government partners dealing with climate sensitive water resources, agriculture, disaster risk reduction, energy, and health to enable them to prepare for and respond for disruptive weather, water, and climate events. Subseasonal to seasonal information includes data, potential risk, vulnerability analysis, assessment, predictions, and longer-term projections as well. I'm not sure how BMKG is doing, but in National Weather Service, which is a part of NOAA, we are strictly defined by mandate to work on subseasonal to seasonal climate information. And also NOAA, Oceanic and Atmospheric Research arm of NOAA, research arm, is working on longer term projections. We can leverage their projections to provide, to include in our services, because our users are coming with this kind of things. So just think how in Indonesia you can adjust this information appropriately. It is subseasonal to seasonal decision support services that enable stakeholders to be climate smart and thus weather ready for the events. When we talk about partners, could we go to the next slide? Thank you. When we talk about climate core partners, we need to clearly define, and right now we're defining them that this would be their partners who enable governmental public safety mission via message amplification. So if we're producing, let's say, a message about a heat wave, our counterparts in United States, like Center for Disease Control and Prevention, can provide their messaging system that it is a heat wave and what should be done. And we are mirroring their messages and providing this kind of like all together across several government agencies. So the message is amplified. It is not only one voice, but multiple voice says exactly the same consistent and repeated message through several voices. General criteria for the core partners is those partners who are directly involved in preparation, dissemination, and discussion involving hazardous weather, water, and climate, and other emergency information, who possess a unique need for increased interaction with national meteorological and hydrological institutions for impact-based decision support services, and have operational nexus, necessitating mutual exchange of data and information to support others. Because we are in federal government agency, we need to really have to provide the information that is within our mandate. When we go to next slide, we can talk about how we vision our climate decision support services. It is a mouthful expression, but I like this one because it is very complete in terms of what exactly we are doing. And we are hoping to achieve a timely, accurate, and reliable suite of subseasonal to seasonal monitoring and prediction products using trusted data, state-of-the-art models, and advances in physical and social sciences to provide impact-based decision support services in easy-to-understand formats with highly trained professional staff for preparedness, response, and climate-related risk reduction. And so I tried with my voice to emphasize the most important parts of the programs that we're doing. And this includes the data analysis, development in models, including social sciences, not only physical science, but the social sciences, to train our staff. And I'm very glad that BMKG is also very serious about training their staff. So we are on the same page with them for preparedness and sponsor climate risk reduction. And when you see this diagram, this kind of like includes the suite of our products, because and how IDSS work. If you would look at x-axis, you can see that climate information starting from the weeks, going to seasons and to the years, works on the preparation for impact-based decision support services, knowing climate risk, knowing what season is coming, what season is going to be like, is important to provide a response and recovery from impact-based decision events. If you will go to the next slide, you can see how WMO is providing guidance for us. Can you advance the slide, please? Thank you. So when we go, this includes these 5 major sectors, I would say, but WMO is called areas of application, which includes health, which includes agriculture, energy, disaster risk reduction, emergency management, and water resources. And this, I like this slide because it kind of like combines how we work together. Because on National Weather Service, we're providing the input into decision support services. It is a left part here, which we provide the data, maps, risk, vulnerability analysis, assessment, and long-term projections and scenarios. Working with our partners from specific sectors, we can derive socioeconomic variables and non-meteorological data that can be combined depending on the user needs. And working together with them, partnering, we can provide the outputs through various different media for dissemination of the messages. If we will go to the next slide, we can see the definitions for all DSS target areas. This is not, of course, complete list. In my further slides, I will include here media because besides agriculture, partners, farmers, emergency managers, energy providers and supply, working in supply, health workers, and water resources managers. Media is helping us to facilitate this message. So we need really to treat media as a special sector or partner in this case to really provide the competent information for them and make sure that the information that we're providing for them is disseminated correctly as well. If we will go to the next slide, this is a summary of science-based decision-making, the steps in the decision. And you can see that decision might be a very tip of the pyramid, because we start with the data. There is a lot of data, and we, through analysis and impact information, we can make one single decision, having a lot of things converging all together into one powerful outcome here. So if we will go to the process on the next slide for decision support services, we can see that weather and water and climate information and observations, it is the data for our green stuff, for the analysis and the models. And what DIC is working in NOAA is on making sure that data for the decision support services are quality controlled, they are consistent, they are clean and nice, trusted data, providing authoritative information. In Weather Service, we're working on making sure that monitoring, analysis, and models are using this data correctly and converging this in the product. And what Cassie is going to show to you is on the green section, how to analyze the data, how to make the information climate services out of this data. Working with partners in the yellow section here, we can assess the impacts and dissemination and communication. The information to our core partners will help them to disseminate these messages correctly. They can include in consultation with National Meteorological Services perception and interpretation to make sure that nothing is lost in communication, and eventually to provide user decision-making and outcomes that would lead to economic and social values for the society. So it is important steps to think how climate information and climate data analysis and outlook products are serving to the bigger picture. When we talk about decision relevant data and information, next slide, please. Thank you. When we talk about decision relevant data and information, I could say that this would be different parts of things, and data, of course, is important things. Information includes analysis, forecast, assessment, and all of this comes with the expert knowledge, because when our partners are not technically savvy in climate terminology, and we need really to make it easy for them to understand. So we need to go through interpretive services to provide expert knowledge and explanation. So we need to work as educators of information and translators of the scientific information for decision support. If we will go to the next slide, please. This will give to you a very good overview for subseasonal to seasonal decision support services needs. What exactly is included. And I was trying just kind of like to give to you a summary of what we found from our engagement with the users. What water resources users need. They need a drought, flood, precipitation, temperature, evaporation, variables, and outlooks and data. For disaster risk reduction, emergency managers need heat, flood, snowstorms in the United States. I know that probably this wouldn't be exactly relevant to Indonesia. Tornado, hurricanes, hail information. For energy, temperature, climatology, trends, degree days, winds, solar insolation. This is all that we can provide for them. Agriculture requires drought, precipitation, temperature, heat, evaporation, and evapotranspiration sometimes too. For health, heat, flood, temperature range, because they can set up the temperature, the climate envelopes for certain disease to flourish, like I'm showing here mosquitoes that are transmitting West Nile diseases and other diseases, vector diseases. And media, we definitely need to make sure that the information is provided well, and definitely interpretation services is very critical here, because we need to work on education of our media partners. And it is definitely includes event outreach, soundbite messages, because they are working with very short, very succinct messages, but this must be a very full and complete sentence that nothing would be left behind. And definitely they need to have, actually not only media, but all sectors need to have impacts and uncertainty. In the United States, we found that through the social media, we definitely can work and reach out to a bigger and longer, broader population of our users to provide these messages. If we will go to the next slide, I would like to talk a little bit here about WMO efforts to provide the decision support services and kind of like equalize the resources and data that are available among all countries. And Climate Services Information System is a big initiative that is provided by WMO. And this includes different enablers, I would say, for climate services information system. And one of them is Climate Services Toolkit that comprise the guidance, data, tools, training, and expert community to support national meteorological and hydrological services to build climate services and develop climate services to have an easy access. Besides that, we have institutions, and National Meteorological Services as a BMKG is definitely a powerful beacon in developing the climate services on the national level. But regional climate centers, global producing centers for long-range forecasting, and experts from WMO community are helping to provide this, to enable climate services at the national level. Besides, there is different activities like ARCOV and National Climate Outlook Forums, world data systems, global seasonal climate updates, intercomparison projects for global modeling, and Cordex are helping these activities to facilitate the information, knowledge, and sharing. So all these resources are helping the countries to develop their climate services at the national level and share knowledge, most important. If we would look at the next slide to see what are the climate services components, I was leading the team who was developing climate services toolkit. So, you know, the rest of the presentation will really focus on climate services toolkit and introduce this to you. This includes online portal. It is most complete source and provides the instant access for the National Meteorological Services. Climate
Sorry,
services. Marina? Yes.
Your time is 1 minute more. Can you maybe make it faster?
I will be very fast. So let's go to the next slide. The next slide provides for you the most important thing, which is, can you go to the next slide, please? Yes, this one. The most important thing from takeaway here is URL for the Climate Services Toolkit. So please explore this one. The rest of the presentation here, it provides for you kind of like a brief highlights of what are the resources, because it includes data training, it includes data access, it includes guidance from WMO. It also builds community through the feedback and question and answers. And the rest of this is giving about the update. And if we will go to the last one, we can see what is the performance evaluation would be. And we, the last slide would be the very last one, slide 21. We'll talk about performance evaluation, and we need to make sure that there is a coverage, accuracy, relevancy to the end users, and efficiency and timeliness in providing the information. Please explore this tool and give me your feedback, and please be in contact with me. You know my email if you need any further assistance. Thank you very much.
Thank you, Marina. So very nice talk, and give us a lot of insight behind what is that decision support services, very important for BMKG as operational agency, similar to National Weather Services there. From Marina, I noted a lot of things, that is the importance of climate information to become a climate smart decision. This is very in need in Indonesia also to be operationally done, especially when we have already a climate early warning system. How we make a climate information really useful for the public. So there are already a lot of discussion in the chat room. I noted more than 10 questions. the feedback from the floor that's already answered by Dr. Dake. So here, I will not repeat again question and answer, but I will give Dick on to summarize all things that already discussed there. What is the maybe questions and also your feedback to the floor, and then we will go to the question for Marina. Please, Dick.
Okay, thank you. So we've been having a good discussion in the chat room about different methods and methods that that are used that weren't part of the presentation. Many of them have to do with some of our extremes tools and how do we define extremes outside of records, which records are a term we use to mean that this event has never happened before. It's the largest of its kind. And the questions a lot had to do with what about extremes that aren't quite unprecedented? They're not unprecedented, but they are very extreme. And we often use a top 10% or bottom 10% category to characterize those kinds of extremes, which is consistent with some WMO recommendations, like the TX90 and TN10 daily temperature ClimDex, if you've used that. So many of our categories, categorical, we discussed a little bit about drought, and many of our drought monitoring and warning systems use categories much like a hurricane or typhoon category system. We have D0, D1, D2, D3, D4, and those are just categories that are applied to percentiles. So D0 means a drought that we would expect about 30% of the time over time. D1 is about 20% of the time, all the way to D4, which is 2% of the time. So we often use the percentile methods to define intensity or unusualness, but we label them with something simpler for the public. And then the last discussion we had was about using percent of normal versus percentiles. And in a wet climate with reliable precipitation, especially during a season, the percent of normal approach is a very good one. We unfortunately in much of the U.S. Can't use that because we have much of the U.S. in season to season has very variable, very high noise, high variability precipitation outcomes. So we often have to, and we often have to go back and convert those to these same percentiles. But I think in a region where rainfall or precipitation totals are a little bit more reliable or larger in a given season, that's a great way to do it. I wish our rainfall was larger and more consistent. So,
okay.
Thank you.
Thank you, Dick. Question for Marina here in the chat room. We can read.
Yeah, I can see a couple of questions here.
Yes.
You know,
please,
one
Marina.
of them. Can you hear me?
Yes. Yes.
One is a question: how long NOAA DSS takes time from observations, processing, and then sharing this to the public? I think, you know, sharing to the public takes this minimal amount of time. Most of the time goes to preparation, and a lot of things has been done in advance. So we are very serious about utilizing and training our staff and using the tools, because sometimes when we talk about decision support services, it is especially in the event deployment, all information must be instantaneous available. So there is a lot of homework needs to be done in advance for our staff to be prepared for this. So we are very serious about making sure that all sorts of tools like Cassie will show to you, like local climate analysis tools that we're developing, like all NOAA tools can be leveraged for decision support services. And they are a lot of online applications, analytical capabilities that can provide the information instantly, because this is critical. Another question here is one of the sensitive sector is climate. For climate information is health. How about the role of COVID-19? I'm actually happen to be a member of the NOAA team on addressing COVID-19. And what we are planning to do is provide the website, kind of like a portal with all information that we have for COVID. And this includes temperature, also moisture, soil moisture, and humidity in the air, that is relevant information, and precipitation. So, you know, most of these things will be put together. This website, web portal is still under development, but as soon as it will be available, I probably would be able to share you so you can see this as an example.
Yeah. So thank you, Marina, for that answer. Actually, I have also a small question to Marina. How about a public expectation, especially millennial generation? Do they really expect it that the information from National Weather Services coming to them through social media as well, and how the NWS manages this issue?
Yeah, good question. You know, we definitely are very seriously looking at expectations from different age generations. Because it actually, this studies, social studies shows that most recently the social media is not playing such a big role. So we need really to address all different ways to communicate and disseminate our information to make sure that it covers all gender and all age communities and population. But definitely there is a emphasis on social media and to see what are the expectations, especially for the millennial generations. We found that they process information much faster and they need a very quick information. So when we're addressing our training materials or education, we definitely are working on more succinct, very 5 minutes summary or explanation. So discrete and succinct information is something that is needed. So we definitely need to address, to converge or to abandon our work on longer lectures to work on the very small but complete soundbite type of information for different generations. Thank you for the question. We're serious about this. I don't think I will give to you a very good guidance yet because it is work in progress.
Yeah, yeah. Oh, there are still many questions to take, and Marina actually in the chat room, but we only have a couple of minutes more. So I will give to take for close statement, and also after that to Marina for close statement. Maybe it's, I hope that it's already covered the rest of the question in the chat room. Please take a close statement from you.
Yes, I very much appreciate the chance to share and to be on this call with you. And I hope our paths cross and we see each other somewhere in the international weather and climate community. Look forward to reading much more about the results of this. I didn't know that this conference happened every year, so I'm very new to this. And thank you for your time and your conversation. And and I hope you have a wonderful rest of the conference.
Thank you, Dick. And from you, Marina, please.
Yes, thank you very much for the question about the media. I really appreciate this because the question is, how do you deal with false reports that or misinterpreted information? So we're using some so-called breach approach. So when we are, and this is a technique that I probably need to teach you specifically, you know, how we do this, that the information would not be used. So when we develop the breach approach, we are taking a first part of the message that we want to bring. Then we step and introduce the reporter name that helps us to avoid the cutting the messages. And then we're bringing the second part. So bridging these two sentences together is helping us to mitigate the erroneous information that is disseminated or translated through from us to through the media. But also when we are producing the reports, we always ask them to send to us the information that we are going to give, and to use the handouts, help us to, with the written statement, help us to minimize this. But, you know, if the information is still slipping through the media that is erroneous, we cannot do really anything about this. So we have just, you know, to assume the responsibility.
Yeah. Thank you.
Thank you.
Thank you for a great lecture, great inspiration from Dick and Marina. Big applause to both speakers, and greeting here from Indonesia. And we will close the session, and thank you for all response, also participation from all participants in the room. And I will give this session back to the committee. Thank you again, and have a good night there in US. Good evening.
Oh,
yeah.
Wait a minute. You know, I'm not sure. How about Cassie's session? It is a different session, or it would be after this? Okay,
Yes,
so
we
we
will
need
have
to
a short break.
log out or stay here.
We have short break and then continue with this link, right, Pak Supari?
Okay.
Yes, yes.
So it would be we don't disconnect, right? So we can stay here put.
Yes.
Yes.
Super. Thank you.
How many minutes, Pak Supari, the break?
5 minutes.
5 minute break.
5 minutes.
And then we continue
Okay.
to do this. Yeah.
Yes. Get your coffee first.
Okay, thank you.
Pak Siswanto, are you ready?
Hmm?
Have you take your copy, Pak Siswanto? Five minutes is enough, I think, Pak Sis.
Okay.
Yeah, so Catherine has already joined with us also.
Yeah. Okay, so everybody in the room, we continue our session to the next agenda. So in the next agenda, we have hand-on training practical sessions. That is how we analyze the extreme climate and data and methodology. With us, we have already here Kathy Smith. She will talk about NOAA climate analysis and plotting tools, introduction, how to create easy plots, and do your own analysis and hypothesis testing. And then Testy will continue to the second part of the talk, that is the NOAA climate analysis and plotting tools practices. So we now start at 9:26, and we will end this session about 10:30. No, 14 minutes past 10, because we already late for kind of 5 minutes. So Kathy, please, time is yours.
Okay. Yeah, my name is Kathy Smith. I work at the NOAA lab in Boulder, Colorado. I've been working there for some number of years. Our group has done climate and weather research. So we look at processes like the MJO, El Nino, things like that. We especially look in the tropics because that's the source of most of the energy for the atmosphere. And it is also important in prediction of weather and climate in the US and around the world. So our group does research. They'd like to be able to do research quicker and easier. So we've developed a set of tools here that can help them look at data and look at relationships between data more quickly and easily. And so I've co-authored some of these tools, and we've gathered them together so users can get to the page and look at data at various timescales and spatial scales and so forth. So I'm going to try to present my PowerPoint now. We'll see if this works. I'll share the screen.
Yeah.
Let's see. And shoot. Can you see it or no?
Yes, it's already come up.
You can see the screen. Oh, the PowerPoint?
Yes.
Oh,
Yes.
okay, great. Okay.
Maybe you can make it, yes. Great.
Yes, okay. So I might toggle back and forth because I'm going to try to show some of the tools live. And if that doesn't work, I'll just show what I have on the page here. So the URL listed is basically a set of the tools we have, a description of each, and then a little picture of a sample plot. Okay, we have various data at our lab. We tend to specialize in reanalysis. So we have the 20th century reanalysis, which goes back to 1836 to near the present, but we also have the NCEP, NCAR reanalysis and various other reanalyses. Reanalysis are basically three-dimensional sets of the atmosphere, all the different variables at one time, and then created over a long series of years. And they use the same model throughout and basically the same data assimilation scheme. So the idea is you use reanalysis, you can look at processes and you don't have to worry that changes are due to the model. We also have ocean reanalysis, same sort of thing, but in the ocean with surface variables. CMIT-5 data, which is basically the forecasts, the climate change forecasts, GFF model, so it's the current analysis. And then we had various gridded analysis data sets, sea surface temperature, precip temperature, OLR, and basically anything we can find that helps us investigate the relationships between, the various components of climate and weather. We also have AMIT model output that's used for a facts page, we call it, that helps you look at climate change and whether you can attribute differences or changes to climate change. We maintain a set of time series, climate index time series, for example, teleconnections like the PNA or the Western Pacific pattern, the NAO and so forth. We also have many El Nino indices, and we basically collect indices. So I know in Indonesia, people are interested in the DMI or the IOD index, so we have that. But basically we collect them and we try to update them, and those are used in our pages. We have some station data, not a lot. We don't tend to specialize in that, and it's a little bit harder to apply tools to that, but we look to add those at some point. Okay, the variables, each data set has its own set, but you have the standard sort of pressure level variables, UV, temperature, J potential, height, and so forth. Temperature, ice, ocean, precipitable water, OLR, fluxes, precipitation twice, no, evaporation. So we do a lot of work on water research. So we try to get precipitation, evaporation, runoff, and soil moisture data. We have SST, lots of different SST data sets going back in time, some very high resolution. We generally produce climatologies of most variables, which enables us to produce anomalies fairly quickly on the fly. And again, we have all the teleconnection indices that we can find. The data sets range from hourly, 4 times, 8 times daily, daily, monthly, and annual. So all different time scales. Spatial scales from very low to very high. The new ERA 5 reanalysis is we have it at 0.25 degrees. So it's pretty good at looking at very local phenomena. And for the ocean depths up to 37 levels for the atmosphere, sorry. And for the ocean, we make available 18 layers. Okay, so again, the purpose of the pages at our lab is to create a set of tools that can look at specific problems and enable people to look at them fast without having to download the data. And you don't have to read the data. The data comes in all these different formats, which is a pain. And so the idea is that you access the data through the web page. You don't have to convert units. You don't have to worry about different latitudes and longitudes or variable names. So it all makes it much easier for the users. We set it up to have climate related features. So we can produce anomalies. When we look at relationships, we often are able to look at lags either before or after. So you can see if an index leads a variable or vice versa. You can step through some of the pages. So you can look at an event and then step through like 6 hours by 6 hours to see how the atmosphere changes. Not listed here, we allow for composites, so averages over different events. So you could average together an MJO from a bunch of different MJOs into a single event or El Nino, and that helps get rid of some of the noise when you're looking at climate and weather features. We try to make plot options enough to make it look nice, and so you can compare data, compare plots. And whenever we do a page, we try to provide statistics. So if you produce a time series, we have all the statistics on the time series. We give you the output files so you can plot them yourself. We give the metadata, citation information, anything like that that's useful to the user. And again, the point is to be able to do quick hypothesis testing and also quick plots. Say, so you're doing a presentation or something like that, and you want to know what January through March temperature looks like. So you can get that quickly. All right, so the first types of tools we have are maps and vertical cross sections. We have one tool that plots all of our gridded data, search and plot. They're kind of generic plots, but it does enable us to look at everything. We have composites, so that's averages, and we have different time scales of those. So you can look at data on sub-daily, like 6 hourly, daily, or seasonal. We have the 20th century analysis, so we have a special set of tools for those composite tools. You can also look at the spread there of the ensemble spread. I don't have a picture here. You have reanalysis intercomparison tools. So in addition to plotting the composites, you can also compare data sets. And we have this tool called FACS, which enables you to look at the AMIP runs and also some of the reanalysis data. Okay. So this is where I'm going to try to do it on the fly. And if this doesn't work, we will go back to this. Let's see here. Okay. All right. So this is the monthly composite tool. So I'm going to look at, I research years where Indonesian rainfall was very high. And so I pulled off a set of 5 years, and I'm going to see if there's a relationship with sea surface temperature. So I'll pull the, can you guys all see this? All right, so I picked the sea surface temperature data set. And these are the years that were high for January. So I'm going to see, is there a relationship with SST data for those years? So I just put those years in for January. I'm going to choose composite anomaly, because that's what I want to look at for sea surface temperature. And I'm just going to plot it for now. And so if this starts taking too long, I'll go back to the talk, but usually it doesn't take too much. Let's see here. Forward click. Okay, so here's the plot. So where you have high precipitation in January over Indonesia, you tend to have a vaguely La Nina looking pattern here with cold temperatures in the central part of the tropical Pacific, warmer temperatures in the Indonesian region. So I can go back, you can experiment, you can do the same thing, you can, but change the variable. So here I'm going to change it to sea level pressure from the reanalysis, and I'll look at the anomaly of that. And so it uses the same options, and it'll plot that. Okay, so there's a sea level pressure plot. I could change the contours to make it a little bit stronger in the tropics because the mid latitudes dominates. I'll go back. Now I'm going to do something. I'm going to go back and look at the sea surface temperature again, but this time I'm going to look at the SST that precedes the January precip by 3 months. So this would be the October sea surface temperature anomaly. Okay, so this, oh wait, this is 3 months after, sorry, I did it wrong. Let's choose this. So 3 months before, so I should have used a negative. Okay, so it's computing. Okay, there you go. So there's the sea surface temperature 3 months before that high precip. And you can see there's no real anomaly in sea surface temperature near Indonesia, but there is a fairly strong anomaly still in the tropical Pacific, and it's more extensive than the concurrent SST pattern. So that might suggest something about the relationship between the two. Okay, I'll go back to my talk. Okay, so those are I did some of those plots. Next, we'll talk about a climate change page. So we have a page that plots the CMIP data and plots the extremes. It's called the Climate Change Portal. And we also have the other facts page that does this. So I'll go back to the web page. Go back to the, what's that? Sorry. All right, I think I'm going to go on the talk and not do more interactive plots for now. All right. It's hard. I've never done it live during a talk. So, okay. So, okay, the climate change forecast for temperature. So this looks at the CMIP models. I plotted it over Indonesia. These are the observed, the historical runs. This is the, let's see, this is the CSM observers. I think I plotted the wrong one. And this is the difference between the ensemble mean and the historic. And you can see it got warmer here. So you can change the variable up in the left corner, change the statistic and so forth, change the region. It can also produce time series at a particular region, which I won't show. We can create time series from all the different gridded data sets on the fly. We can also extract data. So I have some of the tools we have here. And the time series example. So on the left is the, I selected the 20th century reanalysis, air temperature for that from 1920 to 2020. I plotted the region over Indonesia, and you can see that plot on the right here. It generally goes up. There's a strong annual cycle. There's some dips in some places, but it really goes up from the 1950s. And the same plot I just on the lower, sorry, the lower right, I did an annual average just to make that trend more clear. So again, I wanted to look at SST versus precipitation. And here I took the precipitation over Indonesia, which I from the GPCP data set for that same region. And I compared it to the ERSST data set in the central tropics. And you get basically an out of phase relationship. You can also on the web pages use predetermined time series. For example, the Nina 1-2 time series, Nina 3-4, again, a lot of the indices I mentioned. So here I'm plotting that same precipitation data set time series versus the Nina 1-2. And there the correlation was a little stronger, it was minus 0.47. And I can take that same plot, select scatter plot, and instead of getting the 2 time series, I get a scatter plot of precipitation versus SST. So you can see the negative relationship, though it's not strictly linear. Okay, correlations. This is where I correlate a time series that I supply either at a point or area or one of the teleconnections with spatial data. So we have a few different ones of these. We have one related to the reanalysis tools, reanalysis comparison tools, and one based on the NCEP reanalysis data. I'll show the reanalysis comparison tools one. It's a little bit cleaner and newer. So here's a correlation of the DMI, the dipole index, the SST index with SST in the Indonesian region. And you get basically a out of phase between the east and west here. And it was pretty easy to use. I have a September, November, you can change that region around, that time series or time around or whatever you like. Here, again, I'm looking at precipitation versus SST. In this case, it's a correlation, so it's a strict linear one and not a composite. And so you get the same sort of relationship you got before with high correlations with this part of the Pacific. Okay, some random other tools. We have a tool that creates animations from a large number of our data sets on the fly. So you can either do animations and means or anomalies, different time scales, either sub-daily, daily, or annual or monthly, depending on what data there is. You can do Hugmüllers from some of our data sets. So that's time by latitude or longitude at a particular either latitude or longitude averaged. One of our pages looks at the distribution of daily data from a couple of data sets, including the 20 CR. So here's a PDF of the temperature over Indonesia. You can see it's pretty Gaussian. We fit a Gaussian to it on the plot, so you can see how that matches. And then maybe I'll look at statistics. You can also compare distributions in 2 different time periods. So you can, for example, see if the distribution changed or the mean changed over time. We calculate some exotic quantities like EP flux, which I won't talk about. Trajectories, we do trajectories backward and forward from a point using a few different reanalysis data sets. So here's a plot of the trajectory from the nuclear accident in Japan a few years ago. And the colors indicate the level of the flow down below with the key. And so you can see where the air moved to after the accident. We have some specific tools to different events. Like we have a few tools that look at ENSO and how it relates to climate and weather. In this case, it's a risk plot. So what are the odds that you'll get either hotter or colder or wetter or drier values when you have different phases of El Nino. And okay, I don't know how I'm doing on time. So finally, I think I was supposed to suggest possible things that people can try out with our tools. Is that right, Marina?
Yeah.
Okay, so so I came up with some examples that that should be reasonably easy. You can look at El Nino, use the RIT composite or the NCEP composite page, which was from the original first page, and you can enter the years of either El Nino or La Ninas, and you can see what they look like for different variables. You can also go back in time and see what preceded that particular variable you're looking at. We have a page that does extract sub-daily or daily time series from the reanalysis, so you can use it to get something like the highest 20 temperature values for a set of years during a certain month or time period. So you can, and then you can use those dates and put into the composite page to see how those dates look synoptically. For climate change, you can just go to climate change portal and fool around with it, but you can change the area and change statistics, like I said, change the models that are used. For the correlation page, you can look, you can plot correlations with everything. It's always fun to do. I do have a little bit about statistical significance. I'm not sure anybody reads it, but yeah, it's something to keep in mind on the web page that, that just because it looks good, it might not be. And again, we have ENSO risk or composite pages. You can look at the seasonality of the different variables during El Nino. And you can play around with any of the other pages. I guess if you have questions or comments, let me know.
Yeah.
And I'll try to answer them.
Thank you, Katie, for very nice presentations. So it's very useful information for us. I believe that many of us here in the room or participants have been using this PSD tool or PSL tools very long time, especially here. I myself use this PSL portal maybe many years ago, but still I can remember in which part usually I used to use the data and also the analysis. But maybe many participants here also have already experiences, a lot of experiences using these tools. And I've got one question in the room. Can you write the question from Amsari? If you don't mind, can you explain to us how to plot a composite map of OLR anomaly during the dipole mode index, during the dipole mode event, or another climate event?
Okay, could you repeat that question? Sorry. Plot OLR.
Hello?
Yeah. Am I on?
Yeah.
Oh, okay.
Yeah. So I will repeat the question again for you. Can you explain to us how to plot a composite map of outgoing long wave radiation anomaly during the dipole mode event or another climate event which are below or above certain threshold?
Oh, yeah. Okay. I don't think I have the DMI on this, but I'll pick something. So let's go to OLR. Okay, and then I'm gonna pick a time series. What's a good one to pick? Like I said, I don't think I have the DMI on this, but I'll just pick the El Nino. That's always good to pick.
Yeah.
Let's see.
Maybe you can use El Nino there.
Yeah, we're sorry. It's hard to see stuff on the fly. All right. Oh, there we go. All right, so I'll do that. I'm gonna composite on 1.25 sigma. Yeah. So I'll do standardized anomaly. So all the plots should be of the months that are above that. And let's see, let's do anomaly. And it's always scary to do this in front of people. So anyway. Okay, so these are the years it pulled out from that for all the Januaries that exceeded 1.25 sigma. And then, so this is the OLR for that and the anomalous OLR. So these are the years that went into that. So that's how you do that. Let's see, I'll go back. You can also, with this, you can do anomaly instead, or just value, either one. And you can do percentile, which is, I think that works. So you can put in like 90 percentile or something like that. You might not have enough years to get that exact, and it doesn't handle ties and stuff, but that's basically how you do it.
Yeah. Okay, I hope that that answered the question from Amsari. And another question from I cannot see the name there, but in the chat room there is a question regarding the reanalysis resolution there. So NCEP and NCARE analysis is quite coarse resolution. Is there any plan to develop become smoother, finer, let's say like era 40, era, the new era, GRA, Japan analysis, which is about 1 degree?
Yeah, I believe there's plans to produce a higher resolution reanalysis. I believe the current plan is to use observational data that's not satellite data. So you don't get that jump in 1979 to 1980 when you introduce satellite data. But it was going to use a more modern model and assimilate everything else basically aside from satellites. I think that's still the plan. I don't know what the funding or when that's going to come out, but that is the plan. And it would go back before 1979 as well.
Okay.
Most of the reanalysis now started in 1979 because that's when the satellite data is available. Unless you have something like the 20CR or the ERA 20, I think there's an ERA 20C that just uses pressure, and then it uses boundary forcing of ice and sea surface temperature. They go way back.
Yeah, I think this is a very good suggestion to PSL these tools to incorporate with the highest resolution, because some others tools, for example, like Climate Explorer, they already provide kind of the various data that are going into higher resolution, like 0.25 degrees or something like that. So I think because this is very famous portal, the tool, the PSL tools, especially to us in Indonesia and also people in the station there in the region. So I think it is good suggestion to you, to all NOAA's PSL people, to make this very useful with the higher resolution.
Yeah, we do plan on adding the ERA 5 as two composite pages. One issue with the higher resolution is, of course, it takes more time. So something like a map, even if you average a bunch of dates, that's not so bad as far as time, and reading all the data. But if you start looking at correlations over a period of time, or time series, like a global time series, if you want to look at, just the time series, that you have to read every single bit of data to do that. And that's, it just takes the data that's 25 times as big takes 25 times longer. And, people get, it takes, even for the small data sets, it would seem to be taking a while tonight, and those are relatively small. I mean, NCEP and carbon analysis is the one we have is 2.5 degrees. And so 0.25 would, take that much more time to do, which is always a problem. Yeah.
Yeah, thank you. There is a pop-up question from there as well. Are there any certain format or file if we want to use our custom time series in this tool?
Yeah, a few of the pages allow you to upload time series or dates. So the correlation page, I think both of them, and one of the composites, the RIT time series allow you to upload your own time series. So you can compare it to other time series or use it for correlation or composite. You just have to put it in the format that I set. We're looking to do different formats, but it's pretty straightforward. Most people don't have problems with the format. They have problems with their computer, like using Microsoft or something, weird characters. We also have on the composite pages, they can read in dates. So if you have a set of dates, say for a bunch of tropical storms or something like that, then you can read those in, and you don't have to type them in to the boxes, of which we can only supply so many boxes anyway. So you can do that. And you can also create a time series from the page, and it produces it like from the RIT time series page, it produces it in the correct format. So you can pull off, you know, OLR at a point and then use that same time series for correlation or composites later. You don't have to reformat it. It's already in the right format.
Okay, Kathy, we actually already, this is the time for practice sessions.
Oh, okay.
So how we will proceed this session? I saw 5 suggestions from your presentation, the last slide. Can you
Okay. Show
make
that
it-
again? Yeah.
Yeah.
Right.
So do you have any suggestion how we proceed this practical session?
Actually, I wasn't sure because I didn't set it up. If you're able to, you know, if people have devices, they could try the pages out, going to the main page. I don't know how well that works, or laptops, you know, you could do that. I can go back to the page. You can try different things. Look at, if you have your favorite extreme event, you can look at the composites of that, you know, see how that
Okay.
changes over time, something like that.
I have
Cassie, may I
Yep.
suggest, Cassie? This
Yeah.
is Marina.
Please, Marina.
First of all, thank you very much for the great presentations. It is, I think, you know, beneficial for everyone to hear from the developer of the tool, you know, so it is a privilege to have you today. I think, you know, if I may suggest, can you show maybe the first one, how you will do this, and comment how you
yeah, I
will
can do
just
that.
select this, you know,
Sure.
step by step. And, you know, if everybody, all participants on this call will be trying to reproduce exactly what you do, would be beneficial for everyone.
Okay.
Okay, before that, I have also suggestions. So
Okay.
there are 103 participants here. I think they are coming from all regions in Indonesia. So because you have 5 suggestions, so I suggest to all participants in Sumatra, they can choose to practice the first example that Katie will show us, and then the second from Kalimantan, participant from Kalimantan will choose the second practical, the second practice, and then the third, people from Java, and then the fourth, people from Sulawesi, and the rest, people from the east, Maluku, Papua, and also the Nusa Tenggara, Bali, will have a to practice the fifth one. So here, as suggested by Marina, that Katie will show us step by step how to do it. But people from the island that I mentioned, the participant from the island that I mentioned before, can focus in which part they will practice. I think, do you agree with that, Katie?
Sure, that sounds fine. Yeah, and if people have questions, they can ask on the chat. I actually can't see the chat now, unfortunately, so someone else might have to answer or ask me. Okay, so I'm gonna go to go over the first one. Should I wait for that or do that now? The first.
Yes, we can do now.
Okay, all right. Okay, this is basically what I showed before with El Nino, La Nina. I showed El Nino before. I'm going to do this a couple different ways. Let's go to a different variable. Zonal wind looks good. So I can enter years that I remember because I do this too much. So let's see. What's another El Nino year? 1973. Okay. So here I put in 4 years that were that I know are strong El Ninos, and type them in the year. So I have them in January now. I can look at a different season. So I can change this to like JFM. I can plot that. I'm plotting zonal wind at 1,000 millibars at the surface. And right now I'm still compositing on sigma 1.25. Actually, no, sorry. I am not. I typed the years in. So we'll do that. We'll look at the mean first. And I'll keep, let's look and change the region. So I'll do the tropical Pacific. Pardon me. Okay, so I'm going to look at the zonal wind near the surface for strong El Ninos, I guess. So there it is, easterlies, westerlies. I can go back, produce an anomaly. Look at that. Taking a while. Okay, so the same plot, just the anomaly. So you can see the strong westerlies anomalies south of the equatorial region. So I can do the same thing. Let's see, I can, what should I do? Let's look at a vertical cross section now. So I'm going to do zonal wind. I'm going to do El Nino again, but this time I'm going to look at latitude by height plot. And I'm going to keep it an anomaly. So again, plotting an El Nino, what does that look like? So I'll go from minus 30 degrees to 30. So 30 south to 30 north. And I'm going to average over, what's good region? I'll average over the tropical Pacific, say 120 to 200 degrees. And so I'm going to plot the different pressure levels. I'm going to go up to, I'm going to stop it at 100 millibars. So 1,000 to 100 millibars. Actually, I'm going to do the zonal mean. I changed my mind. Okay. So this might take longer. So basically, it's going to produce the zonal mean at every level at the latitudes and that I picked. Oh, I forgot one thing. So this is what happens when you show it in front of people. Latitude by height. So I have different regions you can pick, but there's also latitude and longitude by height. Okay, so there you have a jet high up, anomalous jet, 25 north and somewhat vaguely symmetric to the south. And then over the equator, you have easterlies. Is that right? Yeah, easterlies, anomalies. Okay. And I can do the same thing, just plot the mean. Other things I could do, I've been showing El Ninos. I can show La Ninas instead. It's always fun. So subtract those. This time I'm going to do the composite. So I'm going to get the La Ninas that are less than minus 1.25. So, and I'll do the same plot. I'll do the same zonal average anomaly. Okay. Oh, except sorry. And again, I'm showing it in front of people, so you do less than. Okay, so you get somewhat asymmetric compared to El Nino with easterly jets, easterly anomalies high up, and then a westerly jet, but a little bit further down over the equator. And these are the years that were less than that value. Okay. Okay. So we can change the variable stuff. I won't do that now. Would anybody else like to see anything else with that? Am I on still?
Yes.
Okay, good. All right, I just want to make sure. Okay, so should I go on to the second one or just wait?
Maybe you can go on to the second one.
Sure,
And
okay.
people, a participant from Sumatra Island can just try by themselves to practice your first topic,
Okay.
Mr. Enzo. Yeah.
Okay, all right. So in this case, I'm I use a page that extracts time series from reanalysis. All right, I'll use sub-daily time series. So I'm going to use the reanalysis because it's smaller. I'm going to look at 2-meter temperature over, I'm going to pick Boulder this time. And for August, because that is when, or no, yeah, that was when it was hot. Actually, I'll try September. That was when it was even hotter. So I'll get a subset of dates here. So here I chose the reanalysis, chose 2-meter air temperature at this latitude and longitude. I'm going to put out the highest 20 max temperatures for September. And I'll just use this set of years. Okay. That takes a little while. I should have something that goes around so you can tell it you're waiting, but. Okay, there we go. So for Boulder, Colorado, these were the highest temperatures starting from the bottom. So September 22nd, 2009, it was 271, whatever that is. Anyway, so you can use those, for example, to look at synoptically what a high temperature event looks like by compositing those dates. And you can use this file itself to do that. So I won't do that now. I'll go back. You can also just get the time series itself for that period of time. In the sake of time, I'll get just 1 year. Oh, sorry. Okay, so I have the time series for that point. So you can, it's a way to get the data if you don't know how to read NetCDF at a particular point. And we have, you can change the data sets here. So 20CR, V3, V2C, ERA interim, and ERA 5. And we just have 2 for now, but I'm going to be putting on about 20 more in the near future. You could extract, if we wanted just those at 0Z for whatever reason, we could just pull, select that, and that's all we would get back. You could also, you can get the lowest values as well as the highest, or you can do the same kind of compositing I did before, where you say I want all the values above 1.25 sigma or say 1.0 sigma, something like that. Let's see what we get anything. Okay, so these are the dates that were let's see here. Above that temperature, which is probably all of them. Above that, above that standardized anomaly, which is most of them, but not all of them. Okay. All right. The next thing I had the climate change portal. Oh, actually, maybe we'll use some of those dates to look at different variables. It's just what I had said. So let's go back. Let's get the temperature again. In this case, I'll get the highest 20. So this kind of shows you the problem as data sets get higher resolution in time and space. It can take quite a while to process the whole thing. Okay, so here's a bunch of dates. I'm going to open a new window. I'm going to, let's see, get the list of tools. Sorry. All right, so I'm gonna type in, you can upload this, but I can't do that now. But let's see, it says September 8 at 12Z, and then September 5th, 18Z. September, these are all, I guess there was a warm period during 2013. 6 at 12Z. And then finally one that's not from 2013 to 11/9/1 and 18Z. All right, so it's going to use those dates in the composite just to show you that it is getting the warm temperature all composite on that. And since I'm looking at Boulder, Colorado anomalies, I'll choose the US and I will choose anomaly. So the anomaly is based on the 4 times daily climatologies, 1981 to 2010. So here it is. There's Boulder is actually here. This is gridded data, so it's probably 2.5 degrees, so it's somewhat large, but you can see that you can see the warm anomalies there. You can go back and look at different variables. So let's look at zonal wind at 850 millibars. So those same set of dates. Okay, so not too much interesting here. There's some kind of easterly flow from here, which I guess makes sense, bringing the warm air. Anyway, so you could do that. Again, as I said, you can get the data to plot and so forth. There we go. Okay. All right. You could do the same thing for daily data. And as I said, I could take that file I produced here, this of 20 dates, and I could upload it and then list the file here and give it a title like Hot Days in Boulder. The other thing I can do is I can lag it. So I can say, well, that was the temperature in Boulder, or let's look at the sea level pressure, but instead of looking at the concurrent, let's look what it was 6 hours before. Okay, well, not very interesting, but you could do that. You could go back in time and and see how the warm anomaly progressed. I think it's probably because I picked sea level pressure. I'll try one more. This one might show up a little better. Okay. So strong southerly component 6 hours before that time period. And then looks like synoptically there's something going on, maybe a big ridge right here, which makes sense. You get northerlies and then southerlies here. Okay. We could do that with a 20th century reanalysis too. There's a different page for that I won't show. Okay. Let's go back to our presentation. Okay, the climate change portal. I will go to, let's see, go to that. This is what I was looking for before. Okay. Okay, so the climate change portal. So it has the CMET5 models. You can do the ensemble average, this is the first one. And then there's the different models listed here. It looks like they have about 30 or 40 models. And there's the 2 different RCP experiments. I think it's higher and lower carbon dioxide. It has 5 variables: temperature, precip, SST, maximum temperature. And then it has statistics for each of those variables. I think it's not, the statistics aren't calculated for all variables, but it's calculated for most. So they use the all the ensemble runs to calculate the extreme statistics and the standard deviation. So you have the 10 and 90th percentile. You can also look at the trend or the median. So let's see if I can move this. Time period. Okay, you could set up to do different seasons. This is the 20th century period that defaults to this one, 1911 to 2005. And then you can change the 21st century. So it defaults to the early part, but you can look at the latter part. So here you get, like, again, the observed, the ensemble mean, the observed minus the ensemble mean for the current data, and then the future prediction for that statistic. So if I change the statistic around, I can say, well, how does the 90%, how does the 90 percentile compared to current times change? And plot is up here. Again, these are plotting on the fly, so it does take a while. Okay. All right, so you can see the difference in the days that are above 90% of the current is pretty much higher all around the globe. I don't see any spots where it's lower. So according to at least the ensemble mean, it's going to get more extreme in terms of temperature. Okay, go back. Monthly seasonal plot correlations. This is always kind of fun to do. So I'll go back to that. I'll use the NCEP version. Correlations, sorry. So this page I'm trying to improve. It's on the reanalysis and comparison tool page. It's a little bit better. This was based on the reanalysis, NCEP reanalysis, that starts in 1948, and the one on the other page starts much further back in time. But it's always fun to look at stuff. Let me see here. So let's pick OLR, and what's a good correlation? So let's do something different. Global mean temperature. Okay, actually I'll go back. So you can see it's positive correlation pretty much everywhere for OLR, at least for the Northern Hemisphere. We could change the region, we'll do all. Okay, so you get something like that. Negative correlation in the tropics, positive everywhere else. For correlations, like composites, you can plot vertical cross sections. So let's look at that for air temperature. I don't know what's going to be. Let's do zonal wind, the QBO. We'll do January and latitude by height. Oh.
Kathy,
Yeah.
the moderator seems to have a problem with the internet signal, so
Oh,
it's logged out now. But I will take as a moderator. So
Oh,
we
okay.
have around 12 minutes. So maybe
Okay.
after this, continue with some question already there in the chat room.
Okay. All right. So I'll do one more. As you said, I have a few minutes. I'll do the look at the ENSO.
Okay.
Okay. So this is done. All right. So it's not very interesting. I don't know what it shows. So, but yeah, so you can experiment and see if you see things that you don't know about. Okay, let's look at the ENSO climate risk. So finally, for the last one, we have two ENSO tools. One to look at risk. So that's the odds that you'll get warm relative to cold or wet relative to dry. It's not the same thing as getting as a composite event. So for example, these are on the US here, but for Washington during Washington State during El Nino, you tend to get warm extremes and not cold extremes. See the red here, it's much 90% of the time you get it warmer than normal than the actually 80%. And then in Florida, it tends to be colder during El Nino. So most of the time it's cold. It doesn't mean it has to be very cold. It just is cold compared to warm. So you can change these around. What does precip look like during El Nino? This for the US and so forth. Change the seasons. So it's kind of nice. So this is the US. You guys are all in Indonesia. So let's go back. We also have another page that looks at the globe. These are composite events as compared to risk. So what does El Nino versus La Nina look like for surface meridional wind? So here's the El Nino plot. Here's the La Nina plot, so you can compare them. You can see they're not strictly symmetric or anti-symmetric. We can change variables. One issue with this, these are all pre-calculated. There's been more El Ninos and La Ninas since then. So we could adjust these. For any particular set of years, we'll get slightly different results. So here you see the wet, dry compared to here we have wet on the west and dry on the east. Okay, And, all right, so that's basically it.
Any
Okay.
data?
Okay, I'll go back to, where do I go back to? I'm gonna try to go back to Zoom, see if I can see the chat room. I don't know how to get back to so I can see the chat. Not sure why.
I think you need to tap on your screen, and in this case, it will be a menu showed up, and there is a more option to the right corner. Do the mouse over. I think, Kathy, we lost your audio.
Yeah, your audio is mute.
Oh, now you know. Okay, I'm back. Sorry, I don't know what
Yeah.
happened there. I didn't hit that. So
Already in the Zoom now.
okay.
So you can click on your video, and then there are on the bottom there are mute, video, security, participant, and chat.
Yeah, I should be on. Can you see me?
Yes,
Yeah,
yes.
Okay.
yeah. You
All
can
right.
see on the bottom line there are chat
Okay.
window.
Oh, okay. So I see chat now.
Yeah, you
All
can
right.
see.
Okay. Cordex data. What I heard of Cordex, but I don't remember. Is that rainfall or?
Codec is a coordinated downscaling experiment for climate change.
Oh,
Climate change.
I see.
So this is typically regional climate data.
Yeah. We have some people who have worked with downscale data in our group. I don't think they've made it available in our group for plotting. It would be interesting to do. You, depending on how downscaled it is, you might have to make available just certain regions at a time.
I think Cordex has their own tool for analysis of the data.
Okay.
So please check Climate Services Toolkit. I think they would be linked from there.
Okay. Okay.
Yeah, some of these tools, I mean, on the web, it takes a certain amount of time. So if you ran it offline, you know, it's pretty straightforward. If you ran it online, you have to wait a while when the data sets get really big. That's always an issue.
Okay. So maybe most of participants now is busy with the practical sessions and their own computer. So
Okay.
I tried to read another question. This is maybe not specific for you, but I can read this question is written in Bahasa. There is some participant asking about is there any local wisdom in the US which is used by weather forecaster to, let's say, to identify or to predict some climate events?
Is there any what that's used to predict a climate event?
Local wisdom.
Oh, local wisdom. Yeah, there's always local wisdom. Sure. Yeah, I mean, the climate offices, they sort of actually almost semi-officially, you know, collect that sort of local wisdom. They also have local statistics, which has a name that's I'm forgetting right now, but basically they can run, they take the models at the higher resolutions and are able to run model statistics on it to do predictions locally. So the statistics are tailored for that region. But, you know, there's always, you know, wisdom of what goes on. I mean, forecasters always think, you know, they know the weather in their areas. So.
Can I quickly add to this one?
Mm-hmm. Yeah.
You know, in weather service, what forecasters are doing the best, of course, they are looking at climatology. Because climatology is always a secure thing. So they need to know what are the climatological data to start with and climatological risk. And then they are looking at whether there is ENSO exist, and they're coming to the tools to see what are the local signals. This would be just essential tools for them to look at. And after that, they are going to look at the models and see what is the official forecast for their area is. But for the local information, they can augment with their local climatology and local impacts, trends. Is of course, trend is your friend. Just utilize your trends very well. So a trend is always your friend because it is a good tool. But looking at the trend and relationship to ENSO and other climate variability modes are critical here to know. So this is it.
Yeah. Thank you, Marina, for the additional information. There's one question in the chat room. Kathy, can you read it?
Yeah, thank you. Can you tell us more about how you assess risk analysis? What data do you use? Any in situ data included in the risk analysis? Thank you. So the risk I was talking about for El Nino was somewhat precise kind of risk. So if you expect you expect the temperature to be in the top 20% of the time on average, of course. When you have a certain event like El Nino, you might only see that 10% of the time. So it means that your risk is half of getting that extreme event would be half of what it normally is. And in fact, you could have 0 events as opposed to 20. So I guess that's infinity. But so that's how sort of risk was defined in the context of the El Nino and temperature and precipitation. So we chose a threshold for being above or below, and then saw what during an El Nino, which was defined by another threshold, what were the odds compared to what you'd expect that it was warmer or colder than average or hotter, yeah, or wetter or drier. Risk analysis in general, that I think that might have different meanings depending on how it's used. So I'm not sure I can answer that question. Other than you can do the technique we did for any data set and pretty much in any definition of an event where you know the climatological amount to expect, the climatological distribution. But I don't want to say that that's how you do, quote, risk analysis more generally. If that does that answer the question?
Yeah. Thank you, Kathy. So 1 minute more. Continuing my question about the local wisdom. Actually, in Indonesia, somehow climatologists identify the changing of season based on the behavior of insect. Can you get the point?
I'm sorry, can you repeat that?
Yeah, somehow in Indonesia we identify the changing of season based on the behavior of insect.
Oh, okay.
So the zoo. Is there any kind of this local wisdom also in the US? Maybe this is not.
Yeah, I think so. I mean, there's flowers when they flower.
Yeah.
Stuff like that. When do birds migrate? Just basically lots of natural sort of things like that. And then there's also, when does the jet shift kind of stuff? There's that kind of, more synoptic view of the seasons. But yeah, as far as local wisdom, yeah, I don't know it too well. But yeah, animals and plants, they do change from year to year. I don't know how much they predict, they might just go along with what they're seeing, which might be different.
Okay.
We definitely look quite a bit in NOAA about this specific data, especially in the tribal community across the United States. They have this kind of special data that is associated with blossoming of certain species or some things. And I think it is important for us to incorporate this, especially when we talk about sea ice, and different snow, like communities in northern, in Alaska, for example, have like different definitions of snow that have a meaning, special meaning for them. So it is very interesting, and some scientists are looking at this.
Yeah.
And
Okay.
But there is no across all recommendations, so it is not ready science yet.
People do look at, of course, though, in terms of like climate change, where you have the season moving, so you have, you know, blossoming of plants or trees might be sooner than every year. You know, if you look at, so there are different collections of data like that. I'm sure, I know they are in the US, and I'm certain there are throughout the world. You know, so you can track that sort of thing. It's another, you know, way to check climate change too.
Okay. Okay, thank you, Catherine and Marina. And moderator is already here, Asiswanto.
Yeah, sorry.
I get back to you.
I had a problem with my connection, so I lost several times and out and in to the room. So I'm sorry for that inconvenience. But right now it's already 37 past 10, according to the agenda that we already close to
This session.
the session. Yeah.
Yes.
Okay.
Okay.
So thank you, Paspari, who is handling the session where I was out. So thank you again, Marina and Katie. Thank you, Katie, for a very nice guidance and practical guide to us. And I hope that if we have enough time, I would like to see the work that participants done, and maybe Katie will happy to see it. But due to the limited time, so I'm sorry that we could not show the participants' work. So maybe if Katie provide email, or participant can
Oh yeah.
can reach
Totally.
Katie through email and also report the problem, report the result. I think that is good idea to make this connected, connecting and sustain the communication between the developer of the PSL tools and us, who are the users. So again, thank you very much, Katie, for a very nice guidance and talk, and Marina and also Dick. So thank you a lot for your for our collaboration in this session. So here I'm sorry to if there are many things that may be inconvenience in our session. So we close our session. Thank you. Good evening in America. Good morning in Indonesia, and have a nice day all. Assalamualaikum
you.
warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi.
Yeah.
So,
So Katie is provide email there. Yeah, please everybody, you can
okay.
connect to Katie. Yeah.
Okay. So Katie and Marina, after this we will join to the main room, just like in the morning, to have a formal closing from the Pak Sini and also from the organizer of BMKG Indonesia. So we will close this session and go back to the main room.
Thank you so very much. Yes, disconnecting from this session.
Yeah. Thank you.
Bye.
Bye.
Okay, goodbye, everybody. We go to another room.
Yeah.
Move to the main room.
All participants, we have to move to the main room, just
To
like
the main room. Yeah. Okay. See you there.